Okay, time in databases. Oops. All right, a few little subtopics here. Temporal data types, transaction and valid time, temporal data models, temporal relationships. And I warn you, this will get a bit more vague and hand-waffly as it continues. There you go. So, temporal data types. Unsurprisingly, most relational databases support temporal data types. However, they are mostly, or the standard data, the ones that are provided, are to do with modern time. What is quite modern time? Well, we'll see a little bit in a second what kind of modern time is. So, for example, in Postgres, this is for Postgres, we've got one called a data type called time, which is to do with time of the day, just time of the day. One called date, the date of the year, timestamp, a day and a time, a timestamp Z, which is a day, a time, and a time zone. And we also have an interval data type, which I hadn't looked in great detail, but the definition is between two timestamps. So you can have an interval data type as well, representing perhaps 50 years or something like that. And I suspect it may be any 50 years, or it may be 50 years, the 50 years 1800 to 1850 or something like that. I've never used them. But there is also another type of data type that might be brought in as well, which is called a range or a series data type. And I'm interested in how we might be using these for things like geological data, this ordinal time, which I have a lot of ordinal time to deal with. And what these are, data types are, is a sequence of values which you could use to represent a beginning or an end, or a sequence of observations. Say you had an observation in 1900, one in 1907, one in 1908, and one in 1910, or something like that. So these are series, these are sort of lists, ordered lists, which you could put a year or a date type into, and then therefore get some kind of a data type representing ordinality of times. But these are linked to system time, modern time, database time, and they have limited time ranges. Now, I did have a slide in a previous version of this talk that had these various times, but if you go onto Wikipedia and look at data type range or data type range for temporal variables, you'll find that different operating systems have different beginning dates. So I can't remember. So some operating systems, the earliest date that you could represent as a time date may be about 2,500 years ago. Some of them might be 0 AD. So they have these different time periods. So the further you go back in time, the deeper your time becomes, the less and less useful these data types actually are. So they're to do with modern time rather than deep time, looking at deep time. Databases, there are two types of database time that we're interested in recording in databases. And these are called valid time and transaction time. Now, valid time is what you normally think of as time. It's also known as world time or cartographic time. And it is the time that the thing that you're recording in your database exists in reality in the world. So, for example, my valid time started in 1965 and is going to end in about 40 years' time, or hopefully 40 or 30 years' time, my valid time. So that's the time that we're effective in reality. And that is very much part of the domain model, or data model. And by that I mean the data model that you've designed because you've got a certain set of data, a certain set of problems in a certain domain. So every temporal database is different because it has a different domain design. And time is distributed differently throughout the data model depending on how that data model is organized. And that is one of the fundamental problems with time. We're organizing by space and by entity rather than by time. The other type of time that we're interested in as database people is what's called transaction time. And this is to do with recording how a database itself changes through time. So what it is based on what's called system time, which is the computer time, system time from the computer. And it records when a fact is stored in a database or when it is changed in a database. So it's a record of database history, not a record of the history in the real world. Why is that important? Well, it allows us, it allows traceability in the history of the data set. So perhaps you're a planning authority in the UK, perhaps somebody's put in a planning application, it went in 2 years ago, and since that time, maybe they've had their application rejected, but since that time the database has changed, perhaps new areas of conservation have been designated, perhaps an area has been extended or something like that. But this person is arguing about the information in the case 2 years ago. If you haven't got, you've either got to go back to backup to get a 2-year-old backup, if you own such a thing, off your shelf, dust it down, pray that it operates. I saw a little thing that was flying around Facebook the other week, which is one of these silly throwaway pictures that shows Schrodinger's backup, if you know Schrodinger's uncertainty system. You don't know the state of any backup until you put it in the system and try to get your data back. So what you can do is, if you're recording transaction time, is you record every change in database state, which allows you to rewind the data sets 2 years ago and say, look, this is the situation, this is what the information was 2 years ago, and that allows a sort of traceability and to understand what the information that was actually available at a particular point in time when a decision was made, which may be different from the present day. And this is very much part of the relation to data management system model. So database is provided with tools for managing transaction time. They don't come with tools particularly for dealing with valid time. Although they have tools for dealing with valid time, it's not something that's integral to the database management system. It's something that you have to implement as a user depending on the particular situation. System time. So transaction time gets its time from system time. So what is system time? Well, it's driven by the system clock in a computer. Every computer has a clock that ticks away, and the system clock operates on the number of ticks since an arbitrary starting date, an epoch. So the Unix epoch is the 1st of January 1970. Because that was presumably when the Unix system started to become into general use. Unix, in case you're not familiar with Unix, Unix is the precursor to Linux, the open source operating system Linux. Linux is an open source version of the Unix operating system. In fact, most of the internet is run on Unix, Linux systems, not on Windows systems, not on Apple systems. The majority of large computing operates on Unix and Linux systems. Whereas for Windows, the epoch is the 1st of January 1601. So the system clock is ticking, counting how many ticks, how it counts ticks, I've no idea, since these time periods. So in Unix system time, however many million, that's 1,000 million, 1 billion seconds, translates into a calendar time of 9th of September 2001 at 1:46:40 universal time. And this is important that this system time is linked to those atomic clocks and UTC, and it permits synchronization across distributed databases, these large almost instant financial transactions. Without these system times, without these atomic clocks, the modern internet, the modern financial world wouldn't exist. So in the database, transaction time is simply recorded as a set of discrete events with a timestamp associated, system timestamp. So every time something changes in the database, a T is obtained from the system time and stamped or linked to information on that change. Really importantly, to maintain this system, you have to lock out all historic data within the database. So updates can only ever be made for the current version of the data. If you allowed people to burrow in and start changing transaction times, this sequence of transactions through history, then you are undermining the traceability of the system. So if you made a mistake back here, what you in fact should do is rectify it in the future. You have to rectify it in the future. So you redo the change, basically. You can't go back and undo that change. You have to lock this out. If you want to know the state of a database at time t, at any time, you do what's called roll back the database to the state at t time. It basically goes back through these timestamps, finds the appropriate time, last event, and then reconstructs the database at that time. Postgres has an extension called temporal tables that allows, so that's the example of the Postgres way of providing a general solution, for managing transaction time in a Postgres database. So there is one solution for Postgres databases. There might be another solution for Microsoft, for ArcGIS file geodatabases, and there is. Okay. So what happens? So transaction time, there are different ways transaction time can be recorded. Probably the most common is at the record level. So for example, here's a simple salary database, the employee ID, what their salary is, and we just have fields for the start and the end date effectively for people's salaries. So this is world time. Yep. So these two columns are containing world time. This person got a salary of £25,000, 25,000 in September '93 until the 10th '94. But at the 10th '94, wow, they did pretty well. They got a huge promotion by the look of it. Maybe they took over the company. It doesn't really matter. And they started getting the same employee started getting 50,000. So what happens is, well, in this case, the system time is the system time and the transaction time and the world time are sort of integrated together because you're changing the database when somebody's income changes. This may not act. So this, I said this was world time. It could be world time, but in this instance, we're really thinking about transaction time. But think transaction time. These are happening at the same time that the world time events are changing. So for this record, we have a start date of 9th '93 and an end date of 10 '94. So this record is valid between this time and this time. This record is valid between 4th of '94 and is still valid at the present day. There's no end date here. Similarly for this record, it may be that we have a start date here and it's going on to them. So it's basically with start and end dates at the level of the row to record, to maintain that transaction time. However, we don't have to do it at the level of the row, because if we change, say, one attribute, 20k to 50k, we're having to insert a whole new row and duplicate all the other data in that row that might not have changed. So you're potentially duplicating a lot of data that hasn't changed each time you have a change in your database, yeah? So if that's a problem, you could also implement such a system at the level of the attribute or the geometry itself. So rather than storing when a row start is valid, when it's between the start and end of its valid period, you could do that on each attribute separately. So there are alternative models. That would result in a far more complicated model, but it may be more efficient for data volume stored. So it's a design decision which is the most appropriate approach to take. Now, so that's all I've really got to say about transaction time. Valid time. So valid time is also known as real world or cartographic time. It's all to do with what goes on in the real world. So it's part of the domain model. And it's implemented in different ways, and this is one of the problems. Or maybe it's just inherent to it, but it's a problem. So there's a variety of typographies, classifications of space-time models out there. And over the last week, I've kind of trying to digest these. Well, I've been trying to digest these for years, but I've divided, this is my division, how I divide them up, and this is not necessarily how they're divided up by other people. Maybe I've got a paper to write one day on these things. So I've divided, so there's four, this is what you tend to see, four different models. If you read certainly some of the literature, the older literature, you get these four models, and they're pretty much the same today, but they may be divided up differently. That's all I'm saying. So I'm going to talk about, I divide them into two. I call space plus time models, and then fully spatiotemporal models. So a space-time model is a model of space that you've bolted time onto. A space-time model is an attempt to make a one data model that both incorporates space and time. And it's probably where we want to get to for complex space-time applications, but is still very much sort of in an implementation research environment. They're not generally available as standard database technology. And within each of those, I've got two different divisions: sequential snapshots, continuous time models, base state plus change models, and space-time composite models. And I can explain each one of these now. Sequent time snapshots. In many ways, the simplest model of time, or one of the simple two. These are two simple models of time, and time is discrete in this model because what you're doing is you're having one layer for a time period, or a time. Very straightforward. So one layer for each specified time. So here we go. We've got our XY map. And we've got one layer for each of time, so we change through time. So this is a data model that works well for things like periodic surveys, where you go out and you do one survey a year, for example. You go out and you measure. I've got colleagues who measure the size of snow patches in the Cairngorms, and they measure them week on week, year on year, and they have these time series surveys of the extent of the snow patches. So when you've got periodic surveys, this is quite a good model. Also, if you're calculating periodic statistics that you're distributing to people, it's a good model as well. So for example, monthly average mean temperature, monthly mean temperature at a global level. That's a good model because you calculate for each month, you calculate one layer, and that's what you're talking about. If you're interested in what's going on between these time slices, you're going to need to interpolate. Do you know what I mean by interpolate? Have you done interpolation, spatial interpolation? Is anybody not familiar with the idea of interpolation? Interpolation is just estimating. So you've got measurements around the place. So spatially, you might have a set of observations in space, but you want to estimate a value at an unknown location. That's called interpolation, mathematical interpolation. Well, this is just exactly the same in time. You know where things are at certain points in time and in space, but you want to know what's happening here. You're going to have to sort of do some mathematics that sort of turns this into this somehow, and so that you can guess what the distribution was at the intermediate times. So it's got that disadvantage. But thinking from a topological database management point of view, there are some problems with this approach. It's very simple, it's very useful, but it does have problems. One is that change is not encoded in the data model itself. Okay. And what do I mean by that? Well, there's a lot of data redundancy. Remember data redundancy, duplication. Because where there's no change, we're still recording the same data. So this cell here, or this cell here, is occupied in all 4 models, but it's repeated at those 4 time slices. There is nothing in the data model that's telling us that this square remains the same across those different time periods unless we calculate that it has happened. Yeah? So change must be calculated in this model, and that there is duplication. It's also quite difficult to impose database constraints across this. So for example, if this, perhaps, if there was some other thing that could never occur within this area, then you could have a temporal constraint that said some other thing, perhaps this is a flooding area, I don't know, you can't build certain types of building in a flooding area. You might have want to impose some kind of constraint, temporal constraint. Well, that's very difficult to impose on this kind of, this basic model. There's no change is not integral to the model. So layers, discrete layers is our first one. Now, the second one, my second one is I've called continuous space-time. Now you may see this called a space-time box or a space-time cube. But to me, a space-time cube is just a way of displaying, oops, that wasn't very good. A space-time cube is just a way of displaying the information and not an inherent data structure in itself. So, oops. Here, for example, we're displaying these discrete time layers, sequent times, in a space-time cube. So a space-time cube to me is not a data model, it's merely a way of displaying temporal information. Other people use the word in a different way. So to me, a continuous space-time model is where you record x, y, possibly z, and t coordinates, and you associate them with your space-time object. And that's okay if you've only got one time for each object. So if you had a set of points and you just had one time for each point, earthquakes, this earthquake occurred on this day at this time. If you've got, say, boundaries that only change, that only exist, or a polygon that was a flood extent that was observed at one time, that's all right. But this becomes really more complicated when you've got multiple t's for each object. Then it becomes really a lot more complicated. So if I've got a point, here's an example, these are all points on the left-hand side, a point that exists through time traces a line in space and time. Yep. So these are individuals, this is population movement data. So these are the timelines of individuals through space and time. And in this case, we know we've got an estimate, or we know where every individual was at every time. But these point objects in people, when we trace it through time, they produce linear lines through time. Similarly, if we're talking about spatial lines, they trace planes in time. Polygons trace a 3D solid in space-time, and 3D solids, X, Y, Z solids, trace a 4-dimensional mesh object through the space and time. I don't know how you are at imagining 4-dimensional objects, but it starts to make my head hurt. I can just about manage a 4-dimensional cube, and after that my brain just gives up. So these become quite a difficult data model. Now this data model is in fact very good and is used a lot for visualization. I use it myself a lot. I was going to show you, maybe next week I'm going to maybe talk to you about some of my applications I'm interested in. And I use these space-time points, planes, polygons, and they're great for visualization, but they're not very good. The complexity makes it not very good for querying. It's difficult to query. Certainly by the time where you're trying to query 4-dimensional space-time solids, it really becomes mathematically quite complex, although I'm no expert on the maths. So this is a good model, particularly when you're interested in visualization and to be able to visualize the data, but it's not necessarily a great data to model where if you wanted to query this data. I'm not aware of many tools for, say, querying that kind of data. Again, there is Jason's mentioned. Okay, so there's to a certain extent changes inherent to this data model, but there is no equivalent of sort of spatial topology. So these other models attempt to effectively, what they attempt to do is reduce redundancy is one thing, and to create a integral space-time data model. And there are two basic approaches for doing this. This is the equivalent of adding temporal topology to a data set. So in space, we're talking about topological relationships between things not being overlapping each other or having to connect to each other. Or we can have these same relationships, impose these same relationships in time. To do that, we need an integral space-time model that incorporates those space-time relationships. And these two models are two ways of doing this, and they're illustrated, particularly relevant for sort of polygon data, but it is, these can be implemented with other data types, lines or points indeed as well. So the simplest model, or the simple of the two models, is the base state plus amendments model. So this is a GIS layer. So what we do from the base state plus amendments is we start off with a layer for T0 or T1 it's called here. So maybe the land use type in this example. So we've got two land uses, rural and urban. The colours don't differentiate very well on the screen. Sorry about that. One's a bit yellowy, more yellowy on the computer screen than the other. So we start off in a totally rural environment in T1. Then in T2 we start to get a bit of urban inclusion. So we don't store the whole layer plus with the change like we would in the sequent layer approach. Instead we just store the change. And then at T3 that urban area is expanded out a bit more, and then at T4 we've got some more urban areas coming in. So if we want to know the state of the environment at T3, what we do is we start at T1, we add the change at T2, we add the change at T3, and that's our state at T3. So this provides us with an explicit model of temporal change, which is sort of analogous to topology, spatial topology. It's efficient in that only changes are stored. So we've got rid of the duplication problem. So that's good. We've got rid of the duplication of information. Only changes are stored. It means we can impose temporal constraints because we now know exactly what's happened in a particular place at a particular time without duplication. We've got links between the data layers in space and time, which allows us to implement temporal restraints. But it's a complex data model is required to track these changes, and as the number of edits increases, the effort to reconstruct at a particular time, and most of the time you're interested in the present day, it becomes more and more computationally intensive to reconstruct different times, and that can be a problem. The alternative is called the space-time composite model. So again, we're doing exactly the same model or situation, domain problem, where we've got a change from rural to urban change. So in this case, the colours represent the times at which a change occurred. So at T1, I don't know how clear this is, at T1, this area here, some of this is shaded out because of trying to show superimposed temporal information. So at T1, we had the change was from rural to urban. So we had an urban area in here. Then at T2, it extended out to here, this colour here. And then at T3, we had more urban areas coming in here. And when these overlays are indicating where this urban area has now become back to rural. So what we do is we start again with a base layer at a particular time, T1. And then instead of recording the changes on different layers or sub-layers linked to it, what we do is we chop up the one layer so that all historical, we chop it up into each historical unit. So with each of these changes, we split this main polygon into smaller and smaller polygons. Yep. So we do the same, it's like a giant sort of cookie cutter thing, whereby rather than having the changes stored differently, all in the same layer, this one has changed, so we've now got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 polygons to represent a change through time. We know at what time each of these changes occurred, and that allows us to reconstruct the layer at a particular time. Well, this is all right, it's good, but it involves this progressive decomposition. You're constantly cutting a hole into smaller and smaller parts, which can lead to, certainly when you've got a lot of changes, lots of very small polygons you might end up with. It can have some real problems if you're trying to retroactively edit a data model like this. It can be really quite complicated to do. And of course, like the other model, there's the complexity in recreating the state at different times. To recreate the state, you have to do a sort of complex query to reconstitute the data. So that might be quite slow with large data sets. There is a real, sometimes perhaps maybe a showstopper one for this model, which is that changes are added to a year 0, which you define. What happens if you then get data for before your year 0? You've got to effectively rebuild the model, data model. Think of that, that's analogous to the problem you have with hierarchical and graph databases, where when you change the data in it, you have to reconfigure the whole structure of the tree model behind the data model. So there are problems if you may need to reconstitute this whole data model. Now, this data model is the data model, this composite data model is used. In fact, I suspect all these data models are used, but here's an example of where it's actually used. This is a vision of Britain through time. This is also known, or that incorporates the historical, GB historical database. This is maintained by Humphrey Sutherland colleagues at Portsmouth University. And this is, what it is a collection of historical data for the UK, but in particular the historical changes in census boundaries and administrative boundaries across the UK in modern times. And this, you can see the link there, this is the composite model. Hey, they've implemented the composite model in their underlying database for maintaining these polygonal boundaries through time and the relationships between these census areas and district boundaries and ward boundaries through time. I just point out that they've got start and end dates for their point attributes. Label. Oh, this is an old ArcInfo model, so this predates ArcGIS. This is the data model. Has anybody dealt with coverages, ArcInfo coverages? No, we've got to the generation that don't know ArcInfo coverages. 3 years ago, and you would still know 4 or 5 years ago, you would have still been working occasionally with ArcInfo coverages. They're the data model that predated file geodatabases, and you still might find data in ArcInfo coverages occasionally. But basically, so here's it's a topological model of these administrative boundaries. So the administrative boundaries mustn't overlap in space, but they might overlap in time. And what they do is they record the line attributes, when the division lines between the objects existed, what time periods these line divisions existed, And then what you do is, whenever you want to reconstruct a time, they find the lines, the divisions between the administrative areas that existed at that time period, and then they reconstitute the polygons, the areas from those line files. So they're recording the lines through time, the divisioning lines through time, and then recalculate the polygons on the fly when required. All right, we've got about 5 minutes or so. So temporal relationships. So that's the data model side of things. So temporal relationships. Okay, so we use temporal relationships. Relationships we do use for two things. One is imposing constraints on our data model. The other thing is for querying. So this is a representation of the types of temporal relationships that exist, no space in here, and the types of queries or constraints that you might want to impose on the database, or queries that you might want to ask. So you might want to say, is object A before B, does it meet? Do they share an endpoint and a start point? Do they overlap? These various relationships, does A contain B? You can see these are the various temporal relationships that could exist between objects. And those are nice and simple. Life is simple. You add space in and life gets rather more complicated. So this is by some diagrams by Claremont and Thirrell, so I couldn't pronounce that. Looking at spatiotemporal relationships, the types of spatiotemporal relationships that exist that we might want to impose constraints on or undertake queries on. I'm not going to provide you with answers for how you do this, but we'll just look at this. So remember back to that slide with movement and things like that earlier on. So we've got things appearing, disappearing, or remaining the same, a single entity. We've got entities expanding, contracting, changing shape, or moving or rotating through space. So we've got these spatiotemporal relationships within individual entities that we might want to search for or impose constraints upon. We've got potentially functional relationships between entities in space and time. So in this case, see this square is indicating something happening at a location, and in T1, the white circle is occupying that function in space and time, but in the T2, the black thing, whatever it may be, is occupying that function in space and time. You can also get swapping over of functions in space and time that we might be interested in, permutations of functions. We may have diffusion processes occurring across our system, so we may start with an initial thing and maybe it's producing subversions, so creating different things from itself. I don't know, let's think of an example. So a bomb lands and then there's lots of detritus spread around it as a result. Reproduction, populations, here's a population, then we've got dispersal and the establishment of new populations of a species, something like that. Or we may have a transition situation with disease spread or something like that we're interested in. And then we've got relationships between several entities, so we can have entities that split, that join together, or that change how space is allocated within them. So these are a sort of typology of the types of relationships that we might exist, but it doesn't tell us how we query them. There is no, how you go about implementing those as constraints or as queries, I don't know, there are lots of different ways. So really, really quickly, 5 minutes, time in ArcGIS. As I said, one of the messages I want you to take from this is that world time in GIS and databases is very domain specific. It's done in different ways for in different applications. And that's reflected in the number of tools that are available in ArcGIS for time and their disparity and the way they're spread across the system rather than being in one place, temporal tools. So for example, transaction time, as I say, that's a database DBMS system. So there are systems available for monitoring transaction time in Postgres and in ArcGIS. ArcGIS works, maintains transaction time through a base state plus amendments model, which is called versioning. And what it is you have a couple, it creates a couple of new tables, one called adds and one called deletes tables, and it's in those tables that the changes to the database and the times that they occurred are stored. And then GIS has this thing, I'm not going to go into great details about it, called long transactions, whereby you maybe want to do a lot of work on a certain subset of data and then merge it back into the system. So the transaction time in ArcGIS is also linked to managing these long transactions, which avoid system locks through the system, and then you have to merge your versions back together again. Look that up. I'm not going to go into great details on versioning in ArcGIS. World time. Okay, world time. Okay, how do we implement world time? A common way is to implement it as a time field. That's perfectly normal in a vector table. But you can also implement world time as a field in a raster catalog or raster mosaic data set. What a raster catalog or a raster mosaic are there different ways that you can combine raster data, lots of rasters together with attributes. So you kind of bundle rasters together and put them in a stack, and if one of your attributes of your stack is time, then you can make a sort of one of these sequent piles of rasters quite easily. We can visualize, and then there's a number of tools that are provided that allows to access and visualize the data stored in time fields, including the time slider, the tracking analyst server. They also, in 10.3, have this space-time voxel. Voxel is a 3D raster cell model. This is quite interesting. They store it in netcdf format, which is a multi-dimensional scientific data format. And there's a new thing called the Space-Time Pattern Toolbox that allows you to explore these, build these voxels, space-time voxels, and analyze them. So, have you seen the time slider? Yes, no, yes, yeah. The time slider is very simple. It's a great little tool. I think it's a really good little tool. So what you do is there's a time tab on the layer properties. You set the time field. Then when you click there's one of the icons, this little icon with the clock up, it brings up this slider. You can move, it turns the data on and off with the time slider. It's great for exploring temporal data. But there's also something called the tracking analyst extension. I don't know what's happened, there seems to be psychedelic colors there. So this is a set of tools for exploring and displaying temporal data. So here we've got hurricanes. It allows you to symbolize tracks according to time, things like that. So you've got symbology based on time. It allows you to produce direction graphs and supports a number of other sort of visualization techniques and things like that for particularly movement data. The tracking server, I'll do this one first. This is an add-on, particularly sort of corporate-based information that deals with real-time GIS tracking systems to support things like fleet management, emergency response, resource management. So they have a whole add-in for sort of remote GIS tracking vehicles and stuff like that. This is an interesting one. I was trying to get an example of this and getting it working yesterday, but then I discovered that this tool is only limited to date fields and doesn't deal with integer numeric fields for time, which was really annoying, and I gave up. But what it allows you to do is you take a point set of data with x, y, t coordinates, and then it will build this space-time cube, which is stored in a format called netcdf, which was a scientific data format, not an Esri format. And then you can do things like hotspot analysis and cut into this cube to visualize the data in that field. So I tried to do with that with some of my historic, it's actually data for the speciation events of mammals over the last 165 million years. But I couldn't do it because it required a modern date field, and my dates go back in millions of years, so I couldn't do that. Anyway, nice new tool, need to explore it. Tracking server. Oh, now that's an example of the application that's got out of line. That's an example of the space-time toolbox being applied. In this case, it's to do with so they basically put track to the positions of Matthew, I'm not a tennis fan, and Federer during a match, and then they've used the space-time cube to visualize how the tennis players change their utilization of court space through time through the match. So it's got potentially lots of different applications. Have a look at that one. Okay, so why is time difficult? So as I say, time is kind of difficult. Database time in theory, transaction time is relatively straightforward. There's tools for dealing with that. But world time can be really a bit awkward. And I think my conclusion, which may or may not be right, is, or one of the causes, is that most spatial temporal bases are in fact space plus time. They are not integral spatial temporal models. They're space plus time. You've got a GIS and then you're bolting on some times onto it, which means that time is distributed throughout the domain model. You might have one or more time fields in a table. You might have time fields associated with a data layer, a raster or a vector. In my case, I've got evolutionary trees, so I've got dates associated with the nodes and the branches of tree models distributed in space. You might have time series of records at a particular location in time. So you've got timestamps associated with individual observations in a time series, but also for the whole length of the time series. So you might have time distributed all over your data model. And I think we need a method like we have in PostGIS, where you register the spatial columns and the database, PostGIS knows where the spatial columns are in your domain model. I think we need to do that for temporal columns, and that would allow us to then have functions that dealt with time dependent on the data type being passed into the function, if you understand what I mean. So I think we need a registration system to register temporal fields, and then when you're making a query, the system deals with whether the time is associated with the metadata of a raster or whether it's associated with a field in a vector table. And it kind of does all that data type manipulation behind the scenes rather than requiring the user to know that the time is associated with the metadata of a raster or the metadata of a table, or is this particular field in this particular table. So that's my view. That's how I think we need to move forward.